And then, should we still wait or are we on here? So, today's lecture is supposed to be list colorings. So, in list colorings, yes, for every vertex of graph, what is this? We have a list of colors available for the vertex V. Let's say the list of colors is different. Like let's say here is 1, 3, 5, 7. Yes, this is for V. And then we have. Okay, maybe it's better to write it separately. No. Is some set of colors, yes. And this set for vertex U can be different from vertex V, and usually it's supposed to be like that. They are not all the same. They can common colors maybe in the list, but some vertex has one list, some vertex LU has maybe 1, 2. One, 2, 4, 8, and so on. So, and we usually gonna have, let's say this is part of the graph V, U, and then when we color the graph, we want to choose color LU. Let's say we choose color for U, we choose a for vertex U, we choose a color from its list. So we should assign one of these colors. Let's say 4. And for vertex V, we have to assign some color from this list. Let's say 3. And of course, we like that 3 is different than 4. These colors are differently. One example is, before we go into definitions, there are several definitions. Let's say we have this graph. And let's say the list of colors are here 1, 2, 1, 2, 1, 2, 3, 3, 4, 4, 5. Okay? So maybe we color it by, let's say, choosing here color 1 and put to the vertex to this one color 2 and put to the vertex this color 2. And then here put the vertex color 3. Here put the color 4. And here we have to put color 5. So we have somehow colored our graph. We have colored our graph just to be a little bit more clear. So we choose the colors 1, 2, 3, 4, 5. You see from this new figure drawing, it is a proper coloring. But every vertex gets color from its list. So for this vertex X, the list is 1, 2. And when we make the coloring C of X, we give the color 1, let's say. And similar for every vertex. Okay, now this list L, this function L is nothing but just class of colors. Maybe like this, like 2 on C, like sets from the all colors, yes. And L is called usually list assignment. We assign a list of colors to every vertex. That's mean that. We also call it for V, for vertex V, we also used to call it this set L of V. This is the set of colors where we allowed it to choose a color for this set. Admissible colors. Set of admissible colors for vertex V. Okay. Now what is L coloring? Now we define L coloring. Is a mapping C, let's say, of V I have here in the union of these all colors admissible such that first every vertex the color CV must belongs to its list of admissible colors. Second, for every U and V adjacent, we want C of U to be different from C of V. So we want this coloring to be proper, and every vertex gets color from its list. Then it's a list coloring of graph G. So we define this term. Then we say this. Then we say that C is a list coloring of G. And for G, we used to say, for G, we say G is L colorable. In that case. So if we say graph is L colorable, that's mean for some particular L function that assigned to every vertex a list of colors, we can choose such coloring. L coloring, yeah. Okay. Next, we define the list chromatic number. Also, it's called choice number. Small subtitle. Also call it choice. Have you ever heard of these list colorings? Yeah? Is somebody who doesn't know first time now? Is here somebody who first time listen about? So there are people who doesn't know how many. So we should define all these terms then. Yes. Least chromatic number or choice number is like chromatic number, the smallest number of colors. But now we have lists. For one vertex, some lists can be longer, for other vertex can be shorter, they don't have to be the same. So we have to now make them in a way somehow of the same size, or at least bounded by below. Now we say no chocolates. We say G is k choosable, we define it if G is L colorable for every list assignment with property that size of for every vertex we give at least k colors. Okay? We can also define like a little bit different way. We can say, okay, L is called K list assignment if for every vertex of G. And then we say, okay, G is K choosable if for every K list assignment it admits L coloring. Or it's L colorable, yes. You can also do this way. I used to use that way, yes. So when I started doing PhD, it was like 1996, 7, yes, I started the PhD, something like that. List colorings appear immediately. Become very popular. Because Thomassen proved that every planar graph is 5 choosable, and Margaret Foyt find a graph which is not planar graph which is not 4 choosable. And then they solve it for the equation for the planar graphs, they suddenly become popular. Everybody was doing list colorings. So this is the time my supervisor wanted me to do list colorings for PhD, so I was doing that. Okay, that's the life. It was good. Okay, we have this definition. Now, so what is your opinion? Is it list coloring easier or harder than usual coloring? Why harder? Let's say I have here vertex and I have list of colors 1, 2, 3. And here a list of colors 4, 5, 6. Doesn't matter what I color at U, I can put any color at V, I have no problem. So the lists are more different, should be easier, yes? So why you say usual coloring is easier? So what?
We have restriction on colors.
We have restriction on the
Color.
on the colors. Really? Okay. So maybe you can write. Somewhat, but the way it is true when you have particular list. You know, I can have list very different colors for the adjacent vertices, so it's easy to color it. But you don't ask for particular L. You ask for all L, which are K-list assignments. So, and sometimes it will not be possible to color it. A graph with list of size 2 or 3 or 4, because you will find some particular list which is difficult to color it. One example is like this. This is a, do you recognize this graph? K24. Okay? So I choose here colors 1 and 2. This is my list for this vertex, U. And this is my list for V. It will be alpha and beta. Now in the middle, I have 4 vertices, and for each of these vertices, I will create list of size 2 such that I choose one of these 1 or 2 and one of these alpha and beta, all possibilities. So let's put like 1 alpha here. This is the list of these vertices. 1 beta, 2 alpha, 2 beta. And now, now I have list assignment. To every vertex, I assign 2 colors. And this is, let's be this L. Is this graph list colorable as the list given here? Why not? Because whatever we choose here, let's say color 1, and here color alpha, we have here vertex 1 alpha. Or 2 color beta, we have here vertex 2 beta. Whatever we choose color for U, whatever color we choose for V, when we combine these 2 colors, we have vertex with precisely this list in the middle somewhere. Yes? So we say this graph is not, we can say it's not 2G, this G is not 2 choosable. Or is not 2 list colorable. Okay, we forget to denote it. Or we can say is not L colorable for this list which are given here. And we didn't define it so far. The choice number is the smallest k. Do we have the definition here? Maybe I omit it. Let's say choice number. Do we put this title? No. Choice number or list chromatic number. Okay. I didn't define it. The smallest choice. The choice number or list chromatic number is this. Or list and it is smallest k for which G is k choosable. Okay. So probably for this graph, least chromatic number, I'm quite sure we have no time to play, but you can check as exercise that for this graph, least chromatic number is 3. Maybe we can prove somehow. Maybe we can leave this for exercise for later afternoon.
Part I said. So we take list of size 3. That color will always be available for the other parties.
Yeah, it will be 3, yes? Yes, exactly. We choose whatever we choose here, whatever we choose here. We will have 3 colors here. We will always have 3 colors to color it. This vertex different from here and here, yes? So this is actually very easy. Thanks. This is very easy remark, yeah? Okay. But this graph is too colorable, yes? Which graphs are too colorable? Bipartite. Which graph are two choosable? Which graph are choosable such that every list has size 2? Whatever other lists. It's a harder question. We will not have time to deal with this question. It appeared in the paper of Erdos, Rubin, Taylor. Actually, this was proven by Rubin. The paper has 3 authors, but the theorem inside has only author Rubin. It was a little bit strange just to see that because all authors are equivalent, but probably Rubin needed a result which was done by himself to finish PhD or whatever. And they put his name on this theorem probably. Probably he did it by himself also. And then a regulation at his university, maybe we are fine with that he can finish the PhD. Because some university wants to have standalone paper or standalone result. Not always everything with the supervisor. They say, oh, this was done by supervisor, not by you. Some universities. Is this the case in India? No? Dina? So, in order your student to finish PhD, if he has all his or her paper with you, this one, why? He or she has to have a single author paper?
No, he or she can write paper, he or she can collaborate.
Yeah, but what is the regulation? In order to be fulfilled enough material for PhD. Because sometimes they want to have a single author paper. Or in my university, it is enough to have the author, but no other person on the paper. My university allows papers with the supervisor, but not. You can have also some other paper with other people on the supervisor, but at least one paper just alone or with the supervisor. So this is maybe a reason why this Rubin. Oh, you don't see the slides. Maybe we can upload the slides here. I can upload a little bit the slides. Maybe because you want to be faster, we can use a little bit the slides. This is two choosable graphs, and this is his characterization. This is the author. This is a theorem. Rubin. This theorem appears in paper of Rubin, Taylor, and Erdos. Okay. Maybe we can hide this. So, do you know what is theta graph? Have you ever heard what is theta graph? That means like two vertices, and this is a path of length A, path of length B, a path of length C. This is theta ABC. Maybe I take one example like let's say this is theta, no theta 2, 3, 4. Okay, example of theta graph. And now another definition, core of G. Remove vertices one by one while you obtain graph of minimum degree 2, and this will be the core of G. Remove. Oh. One vertices of G, one by one, until you obtain a graph of minimum degree that will be the core, will be core of G. Let's say, example, let's say we have this graph. This is graph G. What will be the core of this graph? We remove one by one, yes? We remove this vertex. But then this becomes vertex of degree 1. Then we remove this vertex 2. This is now vertex of degree 2. That's okay. I remove this. Okay. This is vertex of degree 2. I remove this, remove this, remove this. So core of G is this, like this. And what if we have like graph like this? What is core of this graph? This is G1. What? We get just vertex. Whenever we have vertex of degree 1, we remove it. Remove it, remove it. And at the end we will get just 1 point. This is not degree 1, this is degree 0. Sorry?
Because minimum degrees to here is not greater than 4.
Or minimum degree, or to be precise, okay. Or by single vertex. I overlook it here because I'm in hurry. So this is the core. Now graph is two choosable, which is like corresponding to two colorable in usual code. Graph is, that's a theorem of Robin, is two choosable if and only if the core belongs to this list of graphs. It is a single vertex, like we get here. It is a cycle of length, even cycle 4, 6, and so on. This means even cycle 4, 6, 8, yeah, because m is at least 1, and then, or it is this theta graph. We have like 1, 2, and we're going to have here, and this is the length is 2m here. So graph, it is characterized. So graph is two choosable if and only if its core is a single vertex, even cycle, or theta of this type, 2 to some even number. Okay, this is the theorem for Rubin. So there is no characterization for three choosable graphs. It is NP hard. So there will be no such theorem. Okay, probably, yes. Okay, we don't have much time. I would like to prove, maybe in the exercise part I will speak a little more, because I would like to prove that, let's use slides because we are very slow. Linear graphs. So Thomassen made his famous proof that every planar graph is 5 colorable, 5 choosable, and so 5 colorable. You know, we did yesterday, we use with the first proof discharging, with the second proof, or with the first proof we use Kempe chains, and with the second proof we use discharging. This proof doesn't use discharging, doesn't use Kempe chain. It's a big thing. It's very simple proof. Crazy idea, very smart idea, but doesn't use anything out of it. So he proved, in order to prove 5 choosability, he makes some assumption on the outer cycle. Some vertices are pre-colored, some will not have list of size 5, but just list of size 3. In order to make, this is like stronger assumption, in order to make induction to work, he did it. And he was lucky, he make it, yes. So what he proved, he proved something like this. Let G be a plane triangulation, near triangulation. Do we know what is near triangulation? Everything inside is a triangles, outside is not. Near triangulation. So all faces are triangle except the outer face. And let's say we have 2 colored vertices, x and y. Color it. So we know how it's C of x and C of y. Okay? And then every vertex on the border has at least 3 colors. So if this is a U, list of U, we assume is at least 3. It can be even 5 and 10, but at least 3. And for a vertex inside, we assume that the list of size 5. So actually we can say the list of these vertices are size 1. Because they are pre-colored, they are colored. When you have list of size 1, it's the same like coloring the vertex. You have to color the vertex with that color. Okay? List of size 1 is the same like vertex is colored. Because you have to take the only color to put it on V. You have no choice. And he proved that triangulation is not necessary to be triangulation, but this is the hardest case. You know, if I have 4 faces, I can put extra H and make my life harder. Because this is the hardest part. If I can color it with H, I will color it without H as well. So inside the triangulation, 1 color, 1, 3, 5. Just sketch. 1, 1, 3, 3, 3, 5. The number of available colors. And he proved if we have like this, we can always color this graph. Okay, let's prove it. I will put some extra. We are here. I will put some extra page. Okay. Base of induction is a triangle. So we have here, let's say color 1, color 2, and we have vertex U has 3 available colors. Maybe he is 1 inside, maybe he is 2 inside, but I have that color X which is different from 1 and 2. Then I put here color X. Okay, base of induction. Do we agree? Do we okay? Now we assume graph has more than 3 vertices and blah blah blah. Case 1. Let's denote this by C. We can assume it's two connected. Okay, it's for simplicity. C is a cycle. Okay. First case. C has a chord. Do you know what is a chord of a cycle? Diagonal, yes? So let's say we have a diagonal. This is C, and this is the diagonal, X and Y. And here the vertex U and V, the vertices U and V, okay? Now, look this graph. Let's say this is C1. And this is C2, okay? Do you see how we do it by induction, by minimality, the big graph? First, list color the graph and use it by C1 and the vertices inside it. I can write it like this. Inner of C1. So we first color this graph. Okay? This graph is smaller. Does it satisfy assumption? Triangulation, your triangulation cycle. Every vertex on the border we have list of size at least 3. 2 colored vertices U and V. Every vertex inside will have 5 colors. Satisfy. So we can color it by induction. So color, let this be G1. Let's call this graph G1. So graph G1 is actually this cycle with everything inside. G1 is smaller than G. We can color G1 by the L colored by induction. So G1 is smaller than G, so we can L color it. Are we done? Yes. Now when we color it G1, what happens? Now what's the next step? What do you think? C2, G2, yes. Now consider G2 graph G induced by vertices on C2 and inside. Does this graph has 2 colored vertices? Yes or no? Do you see here 2 colored 2 vertices? X and Y. Why they colored? Why X and Y colored? Then we can color it after we color this. This will get some color, and this will get color, and these 2 vertices will be colored differently. It's a proper coloring. Okay, so I will say X and Y will play the role of U and V for graph G2. Okay? Are we all agree with this? And now I can apply by minimality induction, and I can color this part. And I have colored, L colored everything. So at the end, it's easy to observe that L coloring, L coloring of G1 plus the L coloring of G2 gives L coloring of G. This was the case when we had the court. Now what is the next case? C has no court. Okay? The next case is C has no court. This was case 1. Now we go to case 2. Case 2. G is chordless. Okay? So let's draw the graph again. Maybe we'll need a new page. How I was putting here, like art page. This is our graph. This is X, no, U. This is V. It's a triangulation, yes? This is C, is chordless. I will take the next vertex to V here. Let it be X. And these two vertices are colored. CU, we have color, and CV. Okay? Now, choose two colors. Choose. Maybe I can move little left this thing. I need space to write here. Okay. Choose two colors, alpha and beta, from LX, from LX minus CV. So look, I have these three colors. Yes? This is LX. At least three colors. Every vertex on the outer cycle has at least. And two of them will be different from CV. So maybe I have here the color CV, then I will have here alpha and beta. Okay? Do you follow now? Is it okay? Now, this is a triangulation, yes? So let's see the triangles around vertex X. Maybe I have like this. And there are some vertices. A1, A2, A3. Here is vertex Y. U. No, Y. W. Y. Y. Okay. What I do? I consider this graph G prime is G minus X. I remove the vertex X. I get smaller graph, yes? Is it too connected? Yes, because I have no chords. So C prime will be like C minus X plus this part V, A1, A2, A3 to this. So let's, C prime will be this. Okay? This is C prime. Okay? Now, I modify list colorings for these vertices. From these vertices inside, they had 5 colors, yes? I will remove alpha and beta. I don't want to have them in the list alpha and beta. I will remove. Okay? And how many colors then I will have for these vertices? At least 5, we remove alpha and beta, and then we will get at least 3. 3 or more. Maybe alpha and beta are not here, and I will still have 5, yes? So my new graph, I will draw it smaller, will look like this. Here is U, here is V, then I go a little like this. L1, A2, blah, 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 A car. I come to U, and then I go like this. I remove X. This is G prime. And this cycle is C prime. It has one less vertex. Do the assumption of the theorem satisfied? We have 2 current vertices. This is a cycle? Yes, it is a cycle because our graph C was chordless. We saw previously the case with chord. And when I remove vertex, what will left outside will be cycle. Because this was chordless, when I remove, I don't get some edge here jumping here. So I will locally, so this will be cycle. This gonna have, they had in G 5 colors, we remove alpha and beta, they had at least 3. This one has also 3 from before, and everything has at least 3. Here where this is we don't touch, they have at least 5. We color this by induction, okay? Color. Color. Now L prime minus color G prime by induction. So we color this graph by induction, yes? We color this graph. Okay? In order to color G, what we should color? We have coloring of G prime, but we want coloring of G. So one more vertex we should color. Which one? X, yes. Let's put it back. Here's X. Oops. Now look. We say we took colors for X. Do you know which colors it were? Alpha and beta. Can we color with one of these X? Look. We remove alpha from these vertices. Yes? So however we color these vertices, alpha and beta are safe. When we choose alpha and beta, we say they are different from the color of this vertex. Okay. So what can happen? It can happen only that this vertex get alpha, we color X with beta. Or this is colored beta, we color X with alpha. Game over. We prove it. That's the 5 choosability of Thomassen. Genius proof, yes, genial proof, how you say it. So we had any arbitrary graph, we make out of it triangulation, we pre-color it to vertices on the outer face, and apply the Thomassen argument. So we 5 color every planar graph. So what left, I want to show the planar graph which are not 4 choosable. That's not. First, it was created by Margaret Foyt. She's from Germany. And second, then several people decrease the number of the minimal non-counterexample, and the last one, which is so far still the smallest one, Mirzakhani. Do you know the name Mirzakhani? So she discovered this when it was she on preparation to mathematical Olympiad she was going, and that was given to this and she found this genius proof construction. She got the gold medal anyway. She got Fields Medal. She went to Harvard, some topology to study and so on, then went to Stanford to work. She got Fields Medal and unfortunately died from cancer. She died on 41, 42, 43 years, so I don't know how much. So this construction is very good. And what he did later is much more. But it was not in graph theory. She did, I think, topology or something like that. So we would like to go. We will use now slides for this because we have huge drawings and it's much easier to see the drawings as they are nicely drawn than my artistic style. Then you cannot do mathematics from my drawings very well. She said like this, look this graph. So we have this vertex x1, x2, x3, x4, x5, and every vertex has 3 or 4 colors. Actually, if you see, this is the outer face. It's a planar graph, of course. This is the outer face. Every vertex on the outer face has 3 colors. Okay? And the vertices inside, this, they have 4 colors. What is the claim? This graph is not L-colorable with this list. Can you help me to prove it? Where should we start? One first observation. I have inside always which colors? So I should not color all these 4 vertices with 1, 2, 3, and 4. Because if I have here 1, here 2, here 3, here 4, I cannot color. So when I have a such square, I should have colored 2 vertices with the same color. And they have to be diagonal. You cannot have like 1, 1 here. Yeah? So here you can have here 1, 1 maybe. Or 2, 2. And then maybe you can color inside. Okay? That's the trick, yes. So we can try a little bit to play. I think we finish this proof, then maybe it will take 5-10 minutes more. I will try to be fast, so I think it's okay. So we finish this Mirzakhani construction, then we will be done for this part of the day. So let's try. Let's say I have 1. Okay. So I think we should go here on this 4 cycle, on this 4 cycle. If I put here 1, here is not 1. So these 2 vertices must be colored. So these 2 vertices must be colored the same in order to color inside, okay? So if here is 1, I cannot put 4 or 3 because I cannot have the same color. So I have to put color 2. So I will put 2 here and 2 here. Then I can choose 1, 2, 2. And 3 and 4, I can choose 4 and 3 or 3 and 4, the same, doesn't matter. Okay, then let's see what happens. So far we have colored this. What happened here? 2, I don't have 2 here. So these 2 should be colored with the same color. 2 is forbidden. 3, yes. So we put here 3. And then we have 3, 2, 1 maybe, and 4, or 4 and 1. Okay, let's go. 3, we have 3 here. I don't have 3 here. So the same trick, I have to 4, only choice, 3 is forbidden, 1, 2, 4. So we choose what? 4, 4. And then we choose, I don't know, 1 and 2, 2 and 1, I think it's irrelevant, yes? And now what here? Oh, no. This one. What should we do here? We have here 4 and we have here 1. If we put here 4, we cannot put here 4. If we have 1, I should put 1 here, yes? 1. And what's now? I cover it? 3. So I cover it or what? I thought I will not cover it.
There is a 1, 2, 3, 4, 2 data that is not.
Yes, okay. I will go to middle. Yes, you look at 1, 2, 3, 4, and you look at the middle. Yes, okay, good. So this is, if we cover that, we started with the 1. So now we start with 3 and 4. We have 2 more cases. We can check another one. We don't have to check all of them. With 1 we do, now we go with 3. If we go with 3, actually, with 1, we go this way. With 3, I think we will go this way, and we will come to here and we will have the same problem. With 3, I think we go with this way, because it's 3, and then we must choose here. Okay, we don't have 3 here, and we choose here 3. In order to be able to choose something here, we should choose here and here some 2. Yes, 2. And then we have here 1 and 4 or 4 and 1, whatever. And then we have here 2. So you see, we go this direction. We have to choose 1, 3, 4. There is no 2. No 2 here. 2 is here. We have to choose. We can choose 2. We have to choose 1. Okay? Do you agree? And then if we go here, when we cover this part, again inside, yes. We are not going to every single step, okay? So you can check at home again if you want this direction. Now what if we choose 4 here? What we get if we choose 4 here? If we got 4 here, I think we should go on the side part. Because we choose 4 here, we don't have 4 here. We don't have 4 here. We have 4 here. We should choose some color which is here and here, but not 4. And this will be 2. 2, 2. And then we have to put like here, I don't know, 1 and 3. 1 and 3 or 3 and 1. Is it the same or irrelevant? I don't know. So if we put here 1, I don't have here 1, then I don't have here 2. There's a problem here, yes? So, and we're done. So if we put 3 and 1, then we don't have here 2, and we don't have here 3, and it will be a problem here. And this is it. Okay, we show that this gadget which has the colors 1, 2, 3, 4, we can name it like M1, 2, 3, 4. Okay? So we don't have to have 1, 2, 3, 4. We can have here alpha, beta, gamma, delta, and correspondingly we get some number, yes? Okay? Now we take these several copies of these gadgets, yes? And we get this one. Can I make it landscape view of this landscape? That this is like this, you know? Maybe, but it's not, okay. It doesn't go like that. I just want it, you know, to see everything at once. Maybe, okay, who is more skilled? I'm not so familiar. So it's good to watch big all of it. Landscape, like this, and we have okay. What you see here, we can go like this. The first part. You see, we have here first part, first gadget. Okay? First gadget. Second gadget. Third gadget. Fourth gadget. Okay? And this gadget here, I think is, where is this? I have also drawn here. Look, the first gadget here, it has letter 5, bigger one. Look this gadget. Everywhere has 5. Do you agree? This is actually M1, 2. If we remove the letter 5, we're gonna have 1, 2, 3, 4. Okay? This is the first M1. When remove color 5, let's write it nicer. When 5, remove it, we get M1. You see, we remove color. Color 5 appears only on the outer vertices, not inside. Not here, not here, not here, not here, not here, and so on. Okay? The second gadget, M2, when color 5 remove it, will be, you see here color 4 is appear big. Color 4 appear big. We consider that color 5 is small here. Okay? So this is actually M5, 3, 2, 1. This is M2. If we remove when 4 remove it from the list, and we see that color 4 appears only on the outer face, yes, nothing inside. Okay, and this coincide, okay, and always on this common edge, it's a grid list, it's carefully selected. Here, M3, here it's M3, then we see here in the third gadget color, which color appear big? 2. We ignore 4 that is big on the border, ignore 3 that is big. 2. So M3 is actually M1435 when to remove it. Okay? And the last thing is we see that color 3 appears big, yes? And so when color 3 remove it, we get that this gadget is actually 2541. Now look, but again, remember that color 3 appear here, but it's only appear on the outer face. Now look, we have this huge gadget, yes? Look, we have an additional vertex. And this additional vertex has list of colors 3, 4, 5. And it's connected with every vertex here. Going around, like this. Okay? This is planar graph, okay? And it has colors 2, 3, 4, 5. So we have to color this vertex. Give me one color of this. 5, okay? If we color it by 5. Look, this is connected with all here, which has color 5. I have to remove color 5 on all these vertices.